Hello and welcome back to the second part of the video on basic continuous time signal. So in the first part of this video, we've looked at 4 out of the 8 continuous time signals that we actually want to look at in this video. So we've looked at the unit step function, we've looked at the unit impulse, we've looked at the rectangular pulse, and then the ramp function, exactly, and every other thing. So now we want to cover the remaining parts in this second video. So if you mix that one, you might need to just check the playlist on Signal and System. So you'll find the link there. All right, so now let's continue. So for on number 5, like I said, we've looked at 1 to 4 in the first part of the video. So, and if you are just coming across this is a lecture series, we also have other videos before this. So every the video on that signal system, just check the playlist on signals and system, you find them there. All right, so now let's continue. The fifth one I want to look at is the Signup function. Okay, all right, so the Signup function is defined as SGN. So again, if you see it SGN, that's Signum function SGM of t is equals to 1 at 1, t is greater than 0, and then at 0 t is equals to 0, and at minus 1 we have our t to be less than 0. Exactly. All right, so now let's look at, so using this now, we can use this to analyze what the signal will look like diagrammatically. So now let's draw our t and our x of t. So don't forget, our x of t is the SGN of t. Okay, so this is going to be our t, and this is going to be our SGN of t, so which is also our x of t, but it's preferable to use the SGN of t since we are talking about signum function. Exactly. All right, so now let's interpret what we are having here into this graph. All right, so the first one says that when it is 1, our t is greater than 0. So let's take this point to be 1. So if this is our 1, and that means our t is greater than 0, so it's going to be a continuous line. Exactly, it's just going to be a continuous line. Exactly, so since they didn't give us a particular value, they just say it's greater than 0. Okay, so that sorts it out. So let's go to the second one. So at 0, this is the point 0 here. Our t is also equals to 0. So it's at this point. So this is 0. So nothing's going to happen here. Exactly, since our t is also equals to 0. Don't forget this line here. This line represent our t, the horizontal line to represent our t. All right. So when our x of t or signum t is at minus 1, so minus 1 will be somewhere here, negative 1. Okay, and we're told that our t is less than 0. Exactly. So once it is less than 0, that's okay. That means it's going to be coming towards this direction. Exactly. So what I just want to do is, so let me just bring this down a bit. So minus 1, so that we can have this line. Exactly. So this that we are having here is that of, so what we are having here is our signum, function. So this is a diagram for so this is a diagram for signum function. All right, so now let's go to the next one. So that's number 6. That's the real exponential function. The real exponential. The real exponential function. All right. So for this now, the real exponential function is defined as x of t is equals to a exponential sigma t exponential raised to the power sigma t. Exactly. So now for this, now there are other things you need to also take note. That's number one. So a and sigma are real numbers. Or let's just put that they are real. Exactly. So now another thing you also need to note is, okay, let me just change the, also if, so if sigma is positive, that means this value that we're having here. Exactly. So if it is positive, so we can conclude that our x of t is growing exponential signal. Okay, is a growing exponential signal. So let me write this properly. So if our sigma is positive, that means this value here, this particular value here, if it is positive, that means our x of t, which is this our x of t, is a growing, and I'm going to show you that in a bit, is a growing exponential signal. But if our sigma is negative, so let me just use this, is negative, so that means our x of t is exponentially decaying. You can say that it is a decaying exponential signal. So you can also say it's a decaying exponential signal. Exactly. And then if our sigma is equals to 0, exactly. So then we can conclude that our x of t is equal to a constant. So you need to take note of all of these 4 points highlighted here when you are dealing with exponential function. I hope that is clear. All right. So now let's look at what they look like in diagram, especially for this growing and decaying exponential signal. All right. So let's start with the first one. So if you have, let's draw our, okay. So let's draw the so let me extend this to this point. All right. So this is our decaying, and this is for growing, which is our B. So for this now, it's going to look like this. Exactly. So this is our T, and this is going to be our X of T. So this is how the graph is going to look like, or this, or the signal, let me call it like that, the signal is going to look like. And then for this, it's just going to go up from here, like this. So this is where our A will be, this is our A. And then this is our T. Exactly. So once you see this, you should know that this is a decaying. And then when you know this, you should know that this is, when you see this, you should know that this is a decaying. And when you see this, you know that this is growing. Exactly. All right. So I hope you find value in this. So let's go to the 7th one. All right. All right. So the 7th one I want to talk about is the Sinc function. So for the Sinc function, so for this is defined as Sinc of t is equals to sine of pi t over pi T. Alright, so is that T or tau? Okay, that should be T. Alright, so this is it for Sinc function. So then don't just think that this can cancel this. So please, it doesn't work like that. So it's just like, let's say you have sine 60 over 60. So then you can't say 60 will cancel 60. Exactly. Alright, so don't think it like that this can cancel this. Exactly. So now let's look at what the diagram for Sinc function look like. So for Sinc function, okay, let me just pause it and draw it real quick. Alright, so this is the mathematical expression, and this is what the diagram will actually look like. So this is our time axis in seconds, and right here is the amplitude. Okay, let me just put it here. So here is the amplitude. Exactly. So this is what the Sinc function actually looks like. Alright, so now let's look at the last one that we're going to be talking about, which is the complex exponential function. So let's put that as number 8. The complex exponential function. Alright, so just like the name complex, but it is defined as x of t is equals to, so let me just give you the mathematical expression for this, x of t. Alright, so I just had to take our time to write it out properly. Alright, so for the complex exponential signal, which is what this particular one is talking about. So complex exponential signal. Now this is the expression x of t is equals to a exponential raised to the power sigma plus j omega of t. Exactly. So we can also rewrite this. This can also be rewritten as this. Exactly. Because of the exponential and the plus. So we're going to be having a exponential sigma of t multiplied by exponential j omega t. Exactly. So this is j omega and then the t right here. Alright. So now using Euler's expression, exponential j omega t, which is this guy here, can also be rewritten as cos of omega t plus j sine omega t. I hope you get that. Now, what was done is that you see this entire thing that is here was replaced with this. Exactly. So this cos omega t plus j sine omega t was used to replace this, and that is what we're having right here. So you can see that x of t is equals to a exponential omega t, which is the same thing as what we are having here. Then this has been replaced with this. Then that's why we're having cos omega t plus j sine omega t. Exactly. So this right here is what we have for the mathematical expression for a complex exponential function. So just for simplification, it says the sine function and the real cosine function can be expressed by the trigonometry identity. That means for this cos omega t, it can also be rewritten as exponential j omega t plus exponential j omega t over 2, and then sine omega t. This is omega, please. This is omega, not ohms. Sine omega t is equals to exponential raised to power j omega t minus exponential minus j omega t over 2j. Exactly. So this is it for the complex exponential function. Well, just like the name complex, it should there's no doubt it's looking a little complex, but if you understand it, you won't have any problem with it. So that is it on basic continuous time signal. So this is the part. So like I said, if you missed the first part, kindly check the playlist on signals and system. And if you have any question or any doubt, do not hesitate to drop it in the comment section below. And so don't forget, this is a video series on signal and system. So the video continues after this, and then we are going to continue from continuous time system. All right, so till then, I'll see you all in that video. So don't forget to subscribe so that you can always get notified as soon as I drop each of these videos. So thank you very much, and I'll see you all in the next one.